In this video, we are going to look at Cahn and God Prelog system of naming enantiomers. Before we proceed, let me give you an example so we see if we can identify any chiral center. Let's take this molecule like this. So you can pause the video and check and see if you can identify any chiral center here. Let me give the second example. All right, so let's take the first one. This carbon has two hydrogens here because it has to form four bonds. One bond to this carbon, another bond to this carbon, and obviously the remaining two bonds, hydrogens. Achiral, achiral, achiral. This one has, this one too, achiral. But wait, let's check this out. This carbon here, it has CH3 bonded. So one group. This is the second group. This is the third group because if you are going here, what you are meeting one on position one is different from what you are meeting on position one here. Over here, if you go here, position one, you meet this and that. Here, position one, you are going to meet this. So one, two, three. Where is the fourth bond? Hydrogen. So this is a chiral center. All right, let's check this out. One, two, three. Obviously, this is also a chiral center, right? Yes, because you can see this group, what you are seeing here when you are coming in this direction is different from what you are seeing here. That's so one, two, and then three. Then the fourth one is obviously a hydrogen. So this is another chiral center. This carbon has two similar hydrogens, so no chiral center, no chiral center. Let's check this out. There's OH here. You know there's hydrogen also somewhere. This is also different from this. So we identified three chiral centers in this molecule. So how many stereoisomers, how many possible stereoisomers can this molecule have? 2 to the power 3 because the number of chiral centers is 3. So it can have up to 8 chiral centers. Let's check this out. Straight, this is chiral. I know you'll be thinking, oh, what about if you draw a plane of symmetry and then you see different things on both sides? No. In 3 dimension, this is pointing away from you, but here this is pointing towards you. So that's why this is chiral. If both of them were pointing away from you, or both of them were pointing towards you, then we can say, well, that's a plane of symmetry. So it is achiral. So this is just a recap on what we did. So since this is chiral, let's try to draw the mirror image to see the eighth enantiomer. So the mirror image, how will it look like? Obviously will look like this. Yeah, so these two are enantiomers. You can see there's no way you can take this and put it on this. Even if you rotate, they can't fit. Non-superimposable mirror images. So, and it's also chiral, so enantiomer straight. All right, so how do we name enantiomers? Cahn and God Prelog system. 4 simple rules. Let's go. So rule one. Sorry, I've added a fifth rule. Okay. So we are going to assign priorities to the bonded atoms. We've identified our chiral center. So the 4 different groups, you have to assign what priorities to them. Good. So we give the one with in terms of atomic number. So if you have the highest atomic number, you take position one, followed by 2, 3, 4. So the one with the least or smallest atomic number will take number 4. Now, if your number 4, the one with the least atomic number, is on your broken wedge, you go ahead and name it. We know that here we can either name R or S. And R means when we trace the numbers we've named, neglecting the 4 and it's clockwise, then we give it R. And then the S is what when we get anti-clockwise or counterclockwise. All right. So if your 4 is on the solid wedge, just give it the opposite name. Maybe after you finish, you had an S, and because your number 4, the one with the least priority, was on the solid wedge, instead of S, you give it R. Now, if your number 4 is in the plane means on the straight line. In our previous video, the very first video I made on the introduction, I made clear the difference between solid wedge, broken wedge in the plane. Good. So if it's in the plane, you do what? That's when you do your rotations. So if you are following this alone without checking to see whether you can do rotations or not, you may sometimes get it wrong. So one thing is that if you always do rotations and make sure your number 4 is on the broken wedge, you're always going to get it correct. Or you just follow these simple rules. Your number 4 is on broken wedge, go ahead. It's on solid wedge, give it the opposite name. It's in the plane, rotate and put it on the broken wedge. It's as simple as that. Now, if you come across double or triple bonds or double bonds, you have to what? Open it up before you go ahead to give assign priorities. So let's take examples. But before we go, we should know some common things and how we can because some things are there you may end up forgetting which one has the highest atomic number. So mostly the halogens shouldn't confuse you. I made a video on periodic table. You can go and watch it out. Halogens. So group 7 elements. So halo means salt. So halogens, the salt form as they form salt, sodium chloride, what have you. So FC Barcelona and Accra. Yeah, fluorine, chlorine, bromine, iodine, astatine. Yeah, so as you are going, the atomic number is increasing. So which of these will have the highest priority is obviously astatine. You see, in that case, it has the highest atomic number. But you'll not be seeing astatine often. You'll be seeing 1, 2, 3, and 4 very often in organic chemistry. All right, let's proceed. Yeah, carbon, oxygen, nitrogen, those things are also there. So the first 20 elements. Just go to my YouTube channel, Dr. Idea Study App. You'll see a video on periodic table and just watch up to the part I spoke about first 20 elements. You can easily get these priorities correct when you watch that video. All right, so let's continue. So we have this. We want to determine if it is R or S. So this is our chiral carbon with 4 different groups bonded. So which one has the highest atomic number? So we look at the chiral carbon. Good. Which atoms are directly bonded? This carbon, bromine, hydrogen, and this carbon. So obviously we can see that hydrogen is the first element, atomic number 1. So it will take number 4 to have the least number. Good. Now you can see bromine, carbon, and carbon. We know bromine is higher, so bromine will take number 1. Now we are seeing carbon and carbon, so we call something breaking of ties. Tiebreaker, yeah, like so you score the same goal, you need a penalty kick to break the tie. All right, so we have to compare. So in breaking ties, this is what you do. This carbon and this carbon are the same. So which atoms are directly attached to this carbon? Directly attached to this carbon. You know there are 2 hydrogens directly attached to this carbon. So over here we have 2 hydrogens directly attached. And then also this carbon is directly bonded to this carbon. All right. Then we come here. Which atoms are directly bonded to this carbon? We know there are 3 hydrogens. Why? Because this carbon is at the terminal end. Covalency must be satisfied. Carbon can form 4 bonds. So 3 hydrogens must be here so that the 4th bond will be here. So here we are seeing just 3 hydrogens. So just compare this and this. You can see that there's a difference. There's one guy who is bigger over here, who is bigger than everybody here, which is a carbon. So this side will take what? Number 2. And this side will take number 3. When you are done, check. Is your number 4 on the broken wedge? Yes, so you can go ahead. You said it's a, if it's on the broken wedge, go ahead. If it's on the solid wedge, give it the opposite name. If it's R, make it S. If it's S, make it R. If it's in the plane, like if it was on any of these dashes, you rotate and put it on the broken wedge. All right. So since it's on the broken wedge, we can go ahead. So forget about number 4. Trace number 1, 2, and 3. So you are tracing 1, 2, 3. This is counterclockwise, anti-clockwise, meaning against the clock. The clock goes like this. So if you are moving the opposite direction to the clock, anti-clockwise, so you make it what? S. So this in Ashima, the configuration will be what? S. So take note of that. Now we know how to name organic compounds, so I'm not going to waste time on that. So you bring your S, then you add a name to it. All right. So let's take the next example. This is our next example. We want to assign R or S to this molecule. Straight, this is our chiral center. So this is number 4. Hydrogen will take the least. This carbon, what are the atoms which are directly bonded to this carbon? You can see carbon, carbon, carbon. We have to break the tie. So let's come to this carbon. Which other atoms are directly bonded to this carbon? Three hydrogens. Good. Let's come to this carbon. Which atoms are directly bonded? Two hydrogens first, then an oxygen. Remember, this hydrogen is bonded to the oxygen. We are not interested in who is bonded to this oxygen. We are interested in which atoms are directly bonded to this carbon here. You see, because it's forming a tie with this, and that. So we are breaking the tie. So atoms directly bonded there, two hydrogens, and then this oxygen. Covalency must be satisfied. One, two, three, four. All right. Then this carbon two, which atoms are directly bonded? Two hydrogens, and then the next one here will be directly bonded. It's a carbon. We are not interested in the other three hydrogens that are bonded to this carbon. We are interested in atoms directly bonded to this. Good. So now comparing this and this, who will take the highest? You can see that yeah, oxygen is here. Oxygen is higher than carbon. Hello, hello. Listen, BBC News on. You come to carbon before you go to oxygen. So oxygen has a higher atomic number. So this side will take number one. So comparing here and here to carbon has a higher atomic number compared to this hydrogen. So this one will take number two. This one will take number three. Oh, but there are hydrogens here too. So why not? Why is it that here still take number two? Obviously, we have somebody who is greater than everybody here. We have somebody who was greater than everybody here and everybody here. So that's why I made it here one, two, three. Is our number four on the broken wedge? Yes. So we go ahead. We don't have problems. Trace one, two, and three. Neglect the four. One, two, three. We are going clockwise. This is R. We've assigned R. As simple as that. Yes, we have this. So straight, hydrogen is our number four, the least here. Now we come to this. Who is the highest? So if you compare FC Barcelona in Accra, obviously bromine is the highest because going down, atomic number is increasing. So bromine will take one, followed by who? Chlorine will take two, and then fluorine will take three. Before you go ahead, check. It's number four on the broken or solid. No, it's in the plane on the straight line. So what do? We have to rotate. We have no option. We have to rotate. We should have even checked this first before we even go ahead and assign priority. So we have to rotate. So keep one group constant and rotate such that your number four goes to the broken wedge. So you can keep this constant and rotate. So we send this is constant, we are holding it, and this one can jump to here. When this one comes here, it's going to push bromine. Bromine to go and push this guy. So in effect, hydrogen will come here, fluorine will come here, bromine will come here. As simple as that. So we have rotated. You could have also rotated anti-clockwise, meaning you would have kept this one constant. Then hydrogen will come here, chlorine will come here, then bromine will go here. So since we went this way, we kept this constant. Hydrogen went here, fluorine came here, and bromine went there. So this is our number four. Number one was who? Bromine. Number two was chlorine. Number three was hydrogen. Sorry, number three was fluorine. So clockwise or anti-clockwise? One, two, three. So this is what? Anti-clockwise. So this is S. We are good to go. Now let's look at the double and the triple bonds. If you have this double bond, you have to open it up before you assign priorities. So this is what you do. Carbon is forming a first bond with oxygen. So you illustrate that. And then a second bond with oxygen again. You bring down two. You are done with carbon. Then now you go to oxygen. Oxygen is forming a first bond with carbon, which is already shown here. And a second bond with carbon again. You bring down two. You've opened it up. If it was triple bond, let me put asterisk on this one. So this carbon with asterisk is forming a first bond with this carbon. Illustrate that. Another second bond. Illustrate that. And another third bond. Illustrate that. So here, opening it up means we want to show only single bonds. Now we come to this one. First bond with this carbon is already established. Second bond, you show it. Third bond, you show it. Then you can now go ahead and assign priorities. So let's take our very last example on this. Yes, we want to assign R or S. We know that there's a carbon here and there's a carbon here. So there's a triple bond between them. Good. So this is our chiral carbon. Obviously, this is number four. It's unbroken wedge. So when we are done, we just go ahead. So we want to break tie because you can see carbon here, and there's another carbon here. These triple bonds are alkynes. If you see carbon bonded to carbon, they are what called alkynes. So alkynes, this is a functional group. So if you see something um, like this, at the end of these three bonds you are seeing, at the ends, there's a carbon here and there's a carbon here. So meaning there's a carbon here and there's a carbon here. Good. So these are chiral carbon. Carbon, carbon, carbon. We have to break tie. Which atoms are directly bonded to this carbon? In fact, we can't break tie. Let's open this up first. So you have to open this up somewhere here. And I think we've already opened it up over here. So I'm going to put asterisk on this one so that it will look as if that was our asterisk carbon here. So this and that over here. We want to open it up. First bond with this carbon, we illustrated it here. Second bond here, third bond here. We come to this one, we do the same. First bond already established, second bond here, third bond here. So which atoms are directly bonded to this other carbon? Three hydrogens. What about this one? Direct bond is what? Three carbons. And here to direct bond to this carbon will be what? This carbon. So which is this direct bond will be what? One, two, and three. Three carbons. Direct bond to this carbon with asterisk is what? One, two, and three. So this is a direct bond. Now let's compare tiebreaker. Who will win here? Obviously, this one will be last, right? So we know we have one, two, and three. So this will always take number three. So these two are fighting between for position one and two. So since we didn't get, if we want to move on to the next set of atoms which are directly bonded to these other carbons, it will just be hydrogens, right? But if we want to move on to the next set of atoms bonded to the next, we want to move on to the next set of atoms, we meet what? Extra two carbons. So extra two carbons fighting against hydrogens. Obviously, this will win. So this is our number one. This is our number two. So one, two, three. We are going anti-clockwise. This is S. This is Cahn Ingold Prelog system of naming enantiomers. If you have an issue with how to name organic compounds, let me know so I make a video on it so that when you get the configuration, you just add the actual name of the compound to it. Thank you.